It is part 2 of section 16.1. In the first part, we defined vector fields. Here, we'll consider conservative vector fields and potential functions. Let's see this recall. F of xy is a differential function defined on a two-dimensional region. Earlier, we defined the gradient using this notation of the function f. So gradient of f is f sub x, f sub y, which is a vector. So we can see now that gradient of f is a two-dimensional vector field defined on a two-dimensional region. Similarly, once f is a function of three variables and differentiable, then the gradient of f is a three-dimensional vector field on three-dimensional region, right? So from now on, we call the gradient of function f and the gradient vector field of f. Okay, let's see this problem. Find the gradient vector field of the function. Okay, so that is f sub x, x derivative, that is 2x and y, and f sub y, y derivative is x squared minus 3y squared. So from here, now gradient of f is f sub x, that's 2xy, f sub y is x squared minus 3y squared, right? Okay. A vector field f is conservative if there is a differentiable function f, little f, such that the vector field is the gradient of function f. So once there is a function such that its gradient is the same as the vector field, then we say the vector field is conservative. In this case, the little f is called the potential function, or simply we say potential. So the gradient vector field is always conservative because it's made from f. So that must be always conservative, right? Now, for this vector field, in earlier, we know that that is made from a function. Okay, let's see, go over there. That is gradient of the function, and so the 2xy and x squared minus 3y squared. So that must be conservative. Now, for this conservative vector field, let's try to find f such that gradient of f is this vector field. Already we know the solution, but let's see how to find little f from given conservative vector field. Okay. Here, if we start with this equation, then that means that this one is first component f sub x, second component is f sub y, right? And then right side, we have here, first component is 2xy, and second component is x squared minus 3y squared, right? So that's the equations we should start with. Okay. Now f sub x is 2xy, which means that f, okay, that is, okay, we number these equations 1 and 2. Then from 1, if we integrate with respect to x, then we can get f. So that is the same as now x squared y and plus a constant. But the constant must be general. So let's say g of y. In this case, if you try to apply x derivative, then that will become 2xy, and this will disappear because it's a function of y. Rather than a real constant k, we are using this general constant. So in some sense, function of y is a constant when we are dealing with x directional derivative, right? Okay, so we have to put this general constant. Now, if we can decide g of y, then that's it. From this one, to decide g of y, we make y derivative. From this one, we make y derivative. Then there is x squared and plus g prime y. That must be same as here, that one, right? And by comparing, we can see that g prime y equals minus 3y squared. So from here, now g of y is minus y cubed, and you have to put a constant. That one. Now g is function of y only, so that you cannot put here a function of x. And if you want to get a constant, then this is a real constant. Okay, so we decided that g of y, and along with this and that, we can conclude here f must be, the first component is x squared y, and the second one is g of y, which is minus y cubed plus k. That's the final answer. Okay. Not every vector field is conservative, and we'll see here an example of non-conservative vector field. Show that the vector field f of xy defined in this way. The first component is this one, and the second component is this one. It's not conservative. We assume in the beginning f is conservative. Then there must be little f such that gradient of f is the vector field, which means here f sub x, the first component, is the same as the first component, and second component of the gradient is the same as the second component of the vector field. So we reject this one. Now we apply y derivative for that one, and then must be 1. If we apply x derivative, then it is 0. Now f sub xy is 1, f sub yx is 0. These are continuous. But earlier, in Clairaut theorem, we know that once second derivative f sub xy and f sub yx are continuous, then 2 must be the same. But right now, they are not the same. That means that this assumption is wrong. Okay? And that's a proof. And later on, we'll study properties of conjunctive vector fields in section 60.3 in detail. Okay. Let's see the problem. At time 1, t is 1, a particle is located at 1, 3. When time is 1, the xy position is 1 and 3. When it moves in a vector field, v of xy is given in this way. Find its approximate location at t is 1.05. After 0.05 seconds later, we want to see approximated location of the particle. That can be computed in this way by using linearization. R of t is now current position and the velocity at the position and time. Okay, that is the approximate location will be produced. Okay. Okay, in the beginning, the location is 1 and 3, right? And then velocity, r prime is velocity, this one. Okay, that one is at 1 and 3. So the x is 1, y is 3, 1, 3. So 3 minus 2 is 1. Now there's a 3. So the 9 minus 10 is minus 1. And time is from 1 to 1.05. So that 1.05 minus 1. So we have here 1, 3. And this quantity is minus 0.05, which is, minus 0.05. And here 1n minus 1, right? Okay. So we can see that, that is plus, not minus, I'm sorry. Okay. And that one will make here 1.05 and 2.95, right? So that this is the approximate location at t is 0.1.05. Okay. Okay. Now here, okay, that is for this problem. I believe it's not so much difficult, and by using here computer algebra system, you may try to get plot. And number 3 and number 4 are quite similar. For this one, you try to get some typical point and try to make the sketch for the vector field. Okay, for this problem, you have to find the right one. Okay, let's consider one of them. Okay, how about D? Then you have to match with the gradient of this function and the figure, the vector field. So that for this one, now gradient of f, which is same as, okay, x derivative will be minus 2x, and that is a sine x squared plus y squared. That is first component. And the second component, y derivative, that is same as minus 2y, and again sine and x squared plus y squared, right? Okay, that's the vector field. So your sine function is fluctuating. X squared plus y squared is r squared. And then along radial direction, it can become positive and negative, so that through radial direction, the vector field is and outward and inward and rapidly changing. So first, you may try to find that one. Okay, among these figures, this one looks like that. So momentarily, you may pick this one for this D. In fact, that's the right answer. You can see detail. Now here, for A, the solution is given. You can check it quite easily. For this one, if you compute the gradient, then now x derivative is e to the y, and y derivative is the same, x e to the y. Okay, for that one. Now, for this one, and once x is positive, so the right side is always positive. This value is positive, that is positive, so that on right side is always, okay, always must be that direction once we have that. And of course, in below also must be given in this range. But this one is go down, so it's not for that one. And also, this is wrong. And already this one is for D. So only the choice is this one. This is the right answer. And also, when x is negative, then y component is negative, but x component is positive, which means that left-hand side, it must be go down anyway, like that. Here, look at this one, really go down. But this one is small because y is less than 0, then the magnitude is very small, so that you cannot see the direction. However, if you try to magnify the vector field, the vectors, then you see such a direction. Okay? So for A, 2 is the right answer. For these two, you may decide yourself. Try. You can get them. Okay? Okay, that's the end of the section. Thank you.